I'm Dr. Pollock. This video is about what a pulsed magnetic field is. So what is a pulsed magnetic field? I'm the author of the book, Power Tools for Health, How Pulsed Magnetic Fields, or PEMFs, help you. So PEMF stands for Pulsed Electromagnetic Field. Now the Earth is involved in a sea of electromagnetism. The sun radiates against the planet continuously. That radiation would normally basically stop life being able to happen on the planet itself. So here's the planet, here's the sun, there's the radiation. The Earth has its own magnetic field, and that magnetic field is compressed on the front because of the radiation. So it's indented by the sun. Otherwise, the magnetic field of the Earth would be pretty large. Because of that effect of the radiation from the sun, the radiation basically bends around the magnetic field that the Earth produces. So this is the front of it, and this is the tail of it in behind the Earth. And there's our tiny little Earth itself. Now, there are four forces of nature. The strong force, which is the force of the nuclear attraction, a weak force, electromagnetism, and gravity. The electromagnetic force is also called the Lorentz force. It acts between charged particles. The greater the charge, the greater the force. Like gravity, this force can be felt from an infinite distance. The electromagnetic force consists of two parts, the electric force part and the magnetic force part. The two are components of the same force. They're inseparable. Electric charges influence each other, and once set in motion, they show the magnetic force. The electromagnetic force also has particles that create a magnetic field around them as they move. So the particles, the electric particles in the universe, which includes atoms, basic atoms, create a magnetic field around them as they are in motion. When electrons zoom through a wire, the wire becomes magnetic. The electromotive force is responsible for friction, elasticity, the normal force of things, push and pull of things, and the force holding solids together in a given shape. Now, the normal force that keeps a book on top of a table, instead of gravity pulling the book through to the ground, it stays on the table because the electrons in the table's atoms repel the electrons in the book's atoms. So the electromagnetic force is around us all the time, whether we are fully appreciative of it or not. So there are two types of magnetic fields: static or stationary or permanent magnetic fields. They're like, say, the fridge magnets or horseshoe magnets or bar magnets. And then there are time varying or frequency or pulse magnetic fields. Time varying means that the field changes over time. That then can be described as a frequency, which we'll get into in a second. Static, stationary, or permanent magnets include shoe inserts, little disc magnets, even electric necklaces and bracelets. This is a typical bar magnet, and these are iron filings. And you can see how the iron filings show you what the magnetic field is like. Basically, the magnetic field around a bar magnet is continuous. We can't see it off the slide or off the picture, but they would, if they could, they'd bend all the way around and come back to the other side. Okay, that's what a standard magnetic field would look like, even with a static magnet or a bar magnet. Now, pulsed magnetic fields are different. Pulsed magnetic fields are produced by a current flowing through a wire. So this is a wire carrying a current. I stands for current, and basically the current is flowing into the wire, and we separate the two wires into a coil. It goes around, basically the current keeps going around the wire, and it comes back and goes back from where it came to close the loop. As current flows through the wire, a magnetic field is generated. This magnetic field is generated according to the right-hand rule. So basically, with a right-hand rule, the magnetic field lines encircle the wire. So if you take the right hand and you take the hand, I put it over a wire conducting current, even a shielded wire conducting current, the current is flowing in the direction of the thumb, and the fingers wrap around the wire. And that's what happens to the magnetic field. You can see the magnetic field circles around just like the fingers would around the hand. They produce basically a continuous magnetic field all the way around space, whether it's an object or through space itself. Now, this is a depiction of a moving magnetic field. Normally, the field would progress down the wire, and as the field goes through the wire, it produces a perpendicular magnetic field. So this is the electrical field, the blue, and this is the magnetic field. It's produced simultaneously. As that current flows down and becomes negative in polarity, it produces a magnetic field opposite it in the other direction, and so on. So the same thing keeps happening. And we'll show you a motion description of this in 1 second. Now, magnetic fields go right through the body like it was air. In other words, they go through air. Air does not block a magnetic field. The body is like air to a magnetic field. It does not stop in the body if the wavelengths are long enough. So magnetic fields go right through the body like it didn't even exist. Wavelengths are determined based on the frequency of the magnetic field. So at 100 megahertz as a frequency, the magnetic field length is about equal to the length of a human body. It's about 6 feet long. Once you get below 100 megahertz, once you get to, say, 50 megahertz, the wavelengths becomes even longer. At 10 hertz, 10 cycles per second, the wavelengths are miles and miles long. So basically, they do not stay in the body. Very high frequency magnetic fields like gigahertz, which you'd see in microwaves, are extremely short. And because they're extremely short, they don't pass through the body. They stay in the body. They get absorbed by the body, essentially. This is a depiction of a magnetic field in air. So what happens is the magnetic field goes in air. It's just passing on through air. But if you put a body in front of it, like in this case, a head, it will continue to pass through the head as if it wasn't even there. So it goes right on through. So you're stimulating the tissues in the body with the magnetic field as it's passing on through the body. Now, when you change the configuration of magnets, say you put two magnetic coils together and you stimulate them at the same time, then basically you're producing a magnetic field that's moving, constantly moving in various shapes and configurations based on the shape of the magnet. And in this case, it's going right through the body again. Show you a good example of how a magnetic field passes into the body.
Demonstrate to you that when I put this on the back of the chair and lean back against the chair, okay, your body will hold it there. Hear that?
Yes.
It's going right through your body.
Wow.
So as I said, magnetic fields pass completely through the body. We rely on that action to be able to treat the entire body. If we get a magnetic field that's strong enough, then it'll as it passes through, it'll stimulate all the tissues and functions in the body if the magnetic field intensity is correct. Now, magnetic waves are described in terms of frequency, which the term we use is hertz, or they're described in terms of pulse rate or repetition rate, or PPS. Now, hertz and PPS are often used synonymously, and that's not right. They're really not exactly the same. And then we should be talking about waveforms. Now, in terms of waveforms, if you drop a stone or something falls into water, you'll see the waves propagating, if you will, from the center of where the waves begin. So you see a series of wave actions, and so you have a crest, and then you have like a trough, and then you have another crest, another trough, and so on as the wave moves on. Measuring the wavelength, you measure from crest to crest. That's also the way you measure hertz, which is cycle per second. So from crest to crest is 1 cycle. And then you measure the number of crests over a period of time, and that gives you the cycles per second, or hertz. This is an example of different types of waves. So this is a sinusoidal wave, and this is like the 0 line in the middle here. So it passes through, goes positive here and turns negative here. This is a square wave, again, passing through the middle. This is a triangular wave, and this is what's called a sawtooth wave. And there are many other examples of different waveforms, but these are some typical waveforms. Now, this is a pulse system. The PEMF 120 produces a very intense pulse, and then it drops off, dies off. But it's this pulse, this strong upward pulse, that determines the action of the magnetic field. So a PEMF 120 coil, or high intensity magnetic pulse system, the repetition rate, the rate at which these things pop, is determined by the pulse rate or the repetition rate. This is a typical sinusoidal wave system, and you can see it crosses through the midline and goes from positive to negative. And that is described, that's the classical definition of frequency, or hertz. Now, magnetic fields lose their intensity as they travel away from the coils, from the applicators. Based on the laws of physics, it's called the inverse square law, or the inverse cube law. Inverse cube law applies to a volume, measuring a magnetic field in a volume, whereas the inverse square law would tell you what the magnetic field is at a point away from the coil. As I mentioned, magnetic fields drop off in intensity very rapidly as you move away from the emitter. So in this area, you'll see the intensity of these different field lines. So this top line, that top line there, is 1,000 hertz, 1,000 Gauss rather, so it's 100 millitesla. Now this is at 1 centimeter away from the coil. So at 1 centimeter, it's 1,000 Gauss, or 100 millitesla. But at 1 centimeter, that magnetic field has already dropped off by about 75%. So it's about 24 millitesla. And it continues to drop off extraordinarily rapidly, so that by the time you reach about 10 centimeters, which is about 5 inches, you've lost almost all of your magnetic field. Again, extremely rapid drop off in the magnetic field. So 1,000 Gauss at about 1 inch into the body would be approximately 7 or 8 millitesla, going from 1,000 down to 7 or 8 millitesla. This is very important when we consider where we want to treat in the body and what magnetic field intensity you need to start with to get the most action in the tissues. This slide is busy, but this slide tells you what the intensity measurements are. So 1 Tesla, and Teslas are typically measured for MRI machines, which are extremely high intensity, but 1 Tesla equals 10,000 Gauss. 1 Gauss is 0.1 millitesla, or 100 microtesla. 1 millitesla is about 0.001 Tesla, and 1 millitesla equals 10 Gauss. 1 microtesla equals about 0.01 Gauss. Very tiny fraction of what a Tesla is. So it's more than, it's a billion, basically a billionth of a Tesla. The Earth itself has a magnetic field intensity of around 0.5 Gauss, or 50 microtesla, or 0.05 millitesla. So it's a half a Gauss on average. It varies a little bit around the planet, but basically it averages out to about half a Gauss. The body's own magnetic fields, and the body produces its own magnetic fields by all the electrical activity in the body, the electromagnetism of the body. And the body's magnetic fields are extraordinarily weak, down to about what we call nanotesla or picotesla. So even much smaller than microtesla. Static magnets typically are measuring anywhere between, say, 1 Gauss and 1,000 or 5,000 Gauss, anywhere between like 1 to 200 millitesla. So depending on the strength of the magnet that you are looking at. Now, intensity matters. The intensity of the magnetic field matters. As I mentioned, the magnetic field, based on the inverse square law, shows that the magnetic field drops off extraordinarily rapidly. Now, there's a video on my website, drpollock.com, on intensity matters. You can search for it on the search box and just type in intensity matters and you'll get to the video. That video talks about these issues again. Now, the effects of magnetic fields on the body are based on Faraday's law. Faraday developed his laws on electromagnetism back in the 1800s. Basically, Faraday's law says that time varying, so in other words, magnetic fields that are in motion, induce an electrical field whose magnitude is proportional to its rate of change. So the amount of charge produced in the body is dependent on the rate of change of the magnetic field. And that is based on something called dB/dt. So here's how it looks. So if this is the intensity of a magnetic field in Tesla, and this is time. So in this case, it's milliseconds. But if you take every waveform produced by a magnetic field is going to take time to reach from its base to its peak. So base to peak. And then it takes time to do that. So if you divide the intensity, the change from 0 to the peak, divided by the change 0 to the time, that will give you the dB/dt. The dB/dt is measured usually in Tesla per second, and the dB/dt determines the amount of charge production in the body. Extremely critical to determine how strong the magnetic field is and how much energy or charge it will produce in the body. Now, the other way that you have to think about magnetic fields too is I showed you the depictions of the coils and how they produce a field around them, and that field then moves away from the coil. Now, the magnetic field configuration needs to be considered. When you purchase a system, you have to have some understanding of where the coils are and what the field configuration is going to be like. So this is an example of some field configuration. So this is an electromagnet or a magnet, and in this case, it's a static magnet. And then the field lines around that circular magnet. If you have a coil with current flowing through the coil in this direction, like a spring, it's going to produce a much more complicated magnetic field. Around each of the wires is where the magnetic field is the strongest. And then between the wires, in the center between the wires, the magnetic field will be very strong, and it'll be weaker as you move away from the wires. This is another depiction with a very tightly wound spring wire, and then how the magnetic fields are produced there. So the magnetic fields around this wire will be stronger next to the wire, as well as whatever it happens to be inside. Most of the time, you're not going to be able to produce something inside it, but then the field lines go away from it. This is another depiction based on the cover of my book, another book that I'd written called Magnetic Therapy in Eastern Europe, a review of 30 years of research. So you can see here's an emitter, and on the surface of the emitter, the magnetic field lines are very tightly packed. As you move away from the emitter, the field lines begin to separate. When those field lines begin to separate, that's when the magnetic field becomes weaker. So very strong magnets will tend to have very dense magnetic field lines. And again, as you move away from the surface of the magnetic field lines drop off based on the inverse square law. And then they connect with each other. So if you have a series of magnets or a series of coils, they begin to interact with each other and begin to add together out in a distance away from the magnet. This is a depiction of how you might be able to treat somebody. So you have to understand your magnetic configuration. In this case, you're putting a body in between a circular magnet. So this person is laying on a flat bed, and this is a circular magnet. So the magnetic field intensity is going to be the strongest in the center of the magnet, but even stronger right next to the coil itself. This is another depiction of a circular type magnet where you're laying on top of the magnet. Again, the field lines are going to be strongest in the center and the magnet. So this is a depiction of a whole body magnetic system with different sets of coils in it, and how those coils produce a magnetic field that moves away from the surface. And as you move away from the surface, the field lines get weaker and weaker and weaker. This is an extremely powerful magnetic system called the Hugo. And basically what you have here in each of these covers is a big wide loop coil. And there's a pad underneath, which is is the same basically. So you're having two of these coils, one on top of the other, and you can produce an extraordinarily powerful magnetic field. This is a depiction of that. So in this case, between those two circular magnets, one above and one below the person, you have a very strong, intense magnetic field, and the field lines spread out around the edges and basically come back and rejoin each other. So that when you pulse the magnetic field, it's basically pulsing out, pulsing out, pulsing out every time you pulse it. So this graphic shows you how each coil produces a magnetic field that peaks and then drops off very rapidly according to the inverse square law. So at approximately, well, half the distance below, it's about 0.75 Gauss, where the two sets of lines basically meet each other. But because you're combining them in this kind of what we call Helmholtz configuration, you're actually producing a magnetic field in between them of about 1.5 times the magnetic field of either one of these. So you get a much more powerful magnetic field when you combine magnets in this way. This applies to almost any kind of magnetic system where you can create what's called a magnetic sandwich. Back to Faraday's law. So a time-varying magnetic field induces an electrical charge. So basically, we're producing every time we have a magnetic field pass through the body. Every time you have a pulse or a frequency passing through the body, a magnetic field is being a charge field is being produced, or the magnetic field produces a charge in the body. So as the magnetic field passes through the body, it induces charge or energy in the tissues that leads basically to all the actions and benefits of PEMF therapy. So PEMF therapy depends on charge production within the body by the magnetic field. This is basically, again, it's Faraday's law, and then you have to consider the other factors that are involved in magnetic fields. So what did we discuss in this video? Number one, the forces of nature, and that's electromagnetism. And electromagnetism is one of the strongest forces in the universe, and it basically goes through the entire breadth and width of the universe. All matter has electromagnetism in it, all matter. There's always the interaction of the electrical charges in the tissues, which is the ions and the minerals and the molecules of the body, and they interact with each other through electromagnetism. We talked about the types of magnetic fields, static and permanent, how a current passing through a wire produces a pulse magnetic field based on the right-hand rule. That magnetic fields go through the body completely. They do not stop in the body, do not get used up by the body. They pass right on through. When the magnetic field frequency, when the wavelengths are long enough, and the wavelengths of microwaves are too short, they stay in the body, and that's why they heat the body. That's why they heat our food in microwave ovens. And we also talked about frequency and waveforms. We talked about the inverse square law, how it drops off extraordinarily rapidly as you move away from the surface of a magnet or the applicator. And a critically important Faraday's law that determines the fact that PEMFs actually work in the body, and different types of ways you can look at magnetic device configurations. How you design the magnetic system will determine what the magnetic field will look like as it moves into the body. And again, the most important thing is that PEMFs induce energy in the body that leads to all the many PEMF actions and benefits. So if you want resources, you can go to drpollock.com. You can get the book, Power Tools for Health, How Pulse Magnetic Fields Help You. We will be producing another website called the PEMF Training Academy, which will be populated over this next year. In addition, if you want to pause this video, you can take down this, this link based on the khanacademy.org, science in their physics area, and they discuss magnetic forces and magnetic fields and magnetic field current carrying wire. So this is a very useful information, and it is very basic instructional information on PEMFs if you want to learn more about it. Thank you for watching. I hope this was informative. Have a great day. Be well.